we can use this same diagram to ask another question. What frequency? So as this particle flies around the loop, how fast? How many cycles does it go per second? So I want to take this opportunity to talk about frequency a little bit. So you're used to thinking of frequency perhaps as f. If you haven't had a lot of physics and a lot of math, frequency is f. It describes cycles per second. And the unit is hertz. That's frequency. That's the frequency we always talk about that we're used to thinking about. We get into physics and we like to use another frequency, omega. We use it to keep up usually with things either going around in a circle, where you might call it the angular velocity. We might use it to keep up with something oscillating up and down just in sinusoidal motion, call it the angular frequency. But we always use omega and not f. Okay? Here's one way to remember it. Frequency f is frequency is cycles per second. Omega is circles per second. Circles per second. What is that? What is a circle? Well, a circle, what's a circle? It's 360 degrees. Oh, but we don't use degrees either. Okay. A circle is 2 pi radians. Okay. So really then, omega we keep up with in radians per second. So if you grew up with hertz and you love hertz, you got to give it up. You got to switch to omega. They're the same thing. There's no difference. Okay? It's really just a factor of 2 pi. Omega in any experiment, any problem you're doing, is always 2 pi times f. Because if one cycle is a circle is 2 pi radians. So you just multiply your cycles by 2 pi and you get omega. Okay? So if you're not used to omega, get used to it, because we're going to be using it a lot. That's what we usually use in physics. Let's ask ourselves then, what is omega here? How do we get omega? In this case, if we can just sort of talk our way through it, we know it's going to depend on how fast it's going, right? It's going some speed v. And how many circles per second is that? Well, you take the speed, how many meters per second it is, say 10 meters per second, and you just divide by the circumference. Right? If it's 10 meters per second, the circumference is 2 meters, that'd be 5 circles per second. So we're going to divide by 2 pi r. Okay? That's circles per second. But we actually do it in radians per second, so we need to multiply those circles by 2 pi. And then you can see the 2 pi's go away. So omega is v over r for any circular motion, actually. So now we can say for this case, we plug in for r. We already solved for r in terms of all these variables. Remember, it was mv over qb. So it's in the bottom, so I wrote mv on the bottom, qb on the top, and that v is still there. But then look, those go away. Okay, so the omega we want, finally, the angular frequency of this thing, of the particle going around the magnetic field, is qb over m. And this is kind of fundamental and interesting because you find that the frequency it goes around has nothing to do with how fast it was going. It only depends on fundamental things to the problem. It depends on the charge of the particle, it depends on the mass of the particle, and it depends on the magnetic field you apply. So if I just take a big smattering of electrons and just throw them into a constant magnetic field, they're all just going to start spinning. And they're all, no matter what their initial velocity is, they're all going to just spin at the same rate, or at the same angular velocity. If I take a bunch of protons and throw them in, they're going to spin at a very different velocity. They have a much bigger mass. If I take two kinds of particles and just throw them in the magnetic field, you can tell them apart because they have different ratios of charge to mass. Okay? So that's one way to identify particles, is how fast do they spin. So since this frequency has sort of this fundamental property, it's called the cyclotron frequency. It doesn't depend on the details of the motion. It doesn't depend on the radius or how it got there or how fast it's going. It really just fundamentally depends on the particle. And you can speed it up or slow it down by adjusting the magnetic field.